Okay, today I'd like to show my research result titled Non-local spin transport in the superconductor ferromagnet hybrid lateral structures. I'm Kohei Ohnishi from Kyushu University of Japan. Then, first I'd like to show the acknowledgement for this work. I worked in the solid state physics laboratory in the Kyushu University, and here is He is Professor Kimura, my boss. Then these students mainly the work for this research project. This is today's outline. The first, I'd like to show the brief introduction of the superconducting spin mechanics of my field. Then I showed for the two experiments. One is for the pure spin current in a normal metal superconducting barrier. And second one, and the spin current in the superconductor, normal metal superconductor, S Josephson junction. Then as final, I show the summary and the small future prospect. Okay, first introduction. As already mentioned for many times in this conference, there's many intermediate phenomena are expected theoretically in the hybrid structure of the ferromagnet and the superconductor. By the interaction of the spin structure of the ferromagnet superconductor, the competition of this, we can the competition made for the intermediate phenomena in the small structure, nanostructure, and these structure can be very useful for the superconducting spin mechanics. Especially indeed in the diffusible regime, these phenomena have the various possibilities for the spinner's application and the speed-related physics. For example, here I show for the infinite for the magnetic resistance and ideal spin source, spin charge separation, and also most recently for the superconducting diode effect are discovered in the Kyoto University in the Ono laboratory and by Ono group. Okay, but however, it is difficult to observe some of these. In some cases, it is difficult to observe these phenomena because in the direct contact ferromagnet superconductor, of course there is superconductivity approximate effect in the ferromagnet, but the coherence length of this proximity effect in the ferromagnet is very short. And also the interaction in the ferromagnet can easy to break for the superconductivity at the interface of the superconductivity at the interface. So it is better we have to tune and control precisely for the exchange interaction in the ferromagnet to measure for the systematically for these phenomena. But in some cases it is very difficult because the ferromagnetic materials have their own for the exchange interaction. And also in the case of the charge current with the spin polarization for there's heating effect. Of course, charge current induced for the Joule heating. So by that, this heating effect can break for the superconductivity of the superconductor. These negative effects make the analysis to be complicated. So today, I'd like to show the other possible way to obtain spin and the Cooper-related signals. Keywords is the pure spin current injection, pure spin current injection, and for the ferromagnet normal metal superconductor tri-layer structure. Okay, shall we go to for the first experiment? Before the explanation of the first experiment, I'd like to show the brief explanation about the pure spin current, because in this pure spin current can be mainly used in this experiment. The charge and spin current can be categorized for the three kinds of the current shown here. First one, unpolarized current, is a very normal, very common current. This current have the only charge component with without spin component. And the second one is the polarized current, usually used in the superconducting spin mechanics. The in the polarized current, the upspin and downspin, in the current, the amount of the upspin and downspin are different. So By this difference, the porous current have charge component and spin component as well. On the other hand, this pure spin current is completely different of these two currents. In the pure spin current, upspin and downspin flows in the opposite direction in the same amount. By this, the charge component is zero in the pure spin current, and there is only spin component. This pure spin current can be induced, usually by the dynamical spin injection or electrical spin injection. The most large advantage of the pure spin current is with no net charge component. By this, we can ignore the heating effect in these structures. And also, especially in the case of the dynamical spin injection, we can fabricate for the wires with no wireless samples to measurement. And also in the electrical spin injection, in the case of the electrical spin injection, for the application we can perform for the non-local spin injection. In this today's presentation, we use negative for this electrical spin injection. Electrical spin injection can be induced by the electrical charge current. Okay. When the charge current flows from ferromagnetic metal to the normal metal, the spin accumulation is induced as the interface in the normal metal layer. Because this is because for the difference of the spin-dependent density of states. This is spin accumulation. This induced spin accumulation can be the flow in any direction of the normal metal layers. So therefore, for example, here in this figure, the left half of this figure, there is only the spin current component, only spin current. So we can say this is a pure spin current. This pure spin current can be recognized as for the 100 polarized current. Okay. So when this pure spin current is injected for the normal metal superconductor interface, intuitively we can consider for the two processes. First process is injected as quartz particles. And second one is for the reflected and projected for the after injection at the interface. This prohibition of the prohibition at the interface is reported by the spin porous current for the 1998. But for the when I start for this project, there is no report for the pure spin current. So in this report, this presentation, I'd like to start from this point. To measure for this projection of the Cooper pure formation at the interface for the pure spin current, we use for the non-local spin current measurement. In the non-local spin current measurement, we use for another ferromagnet for the detector. The point is for the non-local resistance measured by this configuration, probe configuration. The non-local resistance depends on the relative angle of this injector and detector. In the case of the parallel, this non-local resistance have for the high resistance state. So when I sweep for the magnetic field, at some magnetic field, detect one of them that is flipped for the switched, so they change for the anti-parallel state. Anti-parallel state means for the low resistance state. Then by applying the more magnetic field, flip the another magnetization at the injector or detector, so they recover to the parallel state. In the negative state, we can observe for the same feature. So the point is for that by measuring by performing the non-local symbol measurement, we can typically read for the obtain for the magnetic field dependence of non-local resistance like this. The point is for the spin signals. The spin signals is the difference defined by the difference of the non-local resistance in the parallel state and the under-parallel state here. This spin signal is proportional to the for the spin current as detected. So, if the pure spin current is absorbed to the superconducting layer so much, the detected for the pure spin current should be small. So, the spin signal also should be small. But if the pure spin current is prohibited to injected for the superconducting layer, almost all pure spin current can reach for the detector. So, in that case, spin signal should be very large. By this way, we can observe and detect for the how large amount of the pure spin current is absorbed with this superconducting layer. This is actual fabricated devices. These large area, all of these area of the copper nitrogen bilayer, these layer, decoration here. On this large bilayer, we fabricate a small two permanent dot. In this case, we use for the permanent nickel iron. After fabricating for these two dots, we fabricate for these top electrode to reach for these two dots. By using for these samples, first we measure for the temperature dependence of resistance of the copper nitrogen bilayer. By this measurement, as result is shown here. By this, we can estimate for the superconducting transition temperature. Because in the superconducting state, of course, all of the charge current for the nitrogen layer, so these barriers should show for the resistance like this. By this result, we can estimate for in this sample the superconducting transition temperature is roughly 6.8 Kelvin. Okay, so we measure for the spin signals above and below for the 6.8 Kelvin. At 10 Kelvin, this is in normal conducting state. In the normal conducting state, spin signal is very small, 0.17 milliohm. On the other hand, the red line indicates for the superconducting state. We measure the superconducting state at a temperature of 2.3 Kelvin. At that temperature, the spin signal is 0.85 milliohm. Obviously, the spin signal drastically increased in the superconducting state. This can be explained reasonably explained by the schematic shown here. This scenario. In normal state, the pure spin current in the copper is absorbed into natrium due to its strong spin-orbit interaction. Natrium has spin-orbit interaction. So by this, for the pure spin current should be absorbed so much. But in the superconducting state, the superconducting gap initiates pure spin current effectively due to by this superconducting gap. This is completely for the good explanation for the based on the schematic viewing as shown in the introduction. To confirm for this schematic explanation, we measured for the we also fabricate for the sample without natrium layer like this. And the result, the spin signals in these structures, we can observe for the spin signal 0.9 milliohm. This is nearly same as for the 0.85 milliohm, 85 milliohm that in the superconducting state. This result indicates in the superconducting state, almost all pure spin current can flow in the copper layer, then reach for the detector. Moreover, we measure for the temperature dependence of the spin signals. By this temperature dependence spin signals, we can see for the gradual below the TC, the gradual forming of the superconducting gap as the interface. I'd like to emphasize that for this result indicates for the pure spin current can be the good probe for to estimate the superconducting gap as the interface, even for the samples, not the surface, even in the interface in the samples. Okay. To go for the next experiment, we have to change for the viewing of this sample. Change means for the in this samples in the first experiment, we completely for the focus on the pure spin current in this normal meter layers. But in these samples, there is Cooper pair in the superconducting layer. And this Cooper pair should be the proximity induced for the evanesced for the normal meter layer. So in the normal meter layer should have for the proximity Cooper pair induced by the superconducting layer. This means there is a possibility of the coexisting the spin pairs electron and the Cooper pair in the same normal meter layer. To confirm to measure for this situation, we'd like to measure for this situation, but by this structure, we change pretend to your mind for the upside down of this structure. The bottom side for net layers, and the top is for superconductor normal meter bilayers. Okay, in this structure, the pure spin current flow in the normal meter layer, but supercurrent flow in the only superconductor layer. So in this structure, we cannot confirm for in the same time that supercurrent spin current can flow in the same layer. Okay, so to confirm for these two currents can flow in the same layer, we can remove for the superconductor in the top layer. By this, for these two currents should flow in the same layer, but in this case, by just removing this superconductor part, we cannot measure for this supercurrent. So we add for another superconducting part here. By this, we can confirm we can observe the supercurrent in the normal meter layer. This is because the structure is combination of the lateral spin valve and Josephson junction. As you know, as all audience in this conference know, in the Josephson junction, the superconductor, normal metal superconductor sandwich structure, the supercurrent can flow in the normal metal layer because of the proximity effect of the two superconductor part. So but in the combination of this by combination of this lateral spin valve and Josephson junction, we can measure for the spin current and supercurrent in the same structure here. This is actual fabricated sample. This orange the two wire cobalt iron aluminum is ferromagnet, schematic shown here. Then this green area is for the niobium copper bilayer, and only this for the red area is have only copper layer. It's just a bridge for the two ferromagnet and the niobium, these two layers. In this structure, we can evaluate for the Cooper pair transport by the either characteristic of Josephson junction, top side. Then, and also we can perform the evaluation of the spin transport by the normal spin valve measurement by the bottom side. Before the actual measurement, for the first we measured for the temperature dependence of the resistance of the niobium copper bilayer and Josephson junction to confirm for the transition temperature of the Josephson junction and the niobium layer. Without the junction, just bilayer, the transition temperature is 5.8 Kelvin. This red line indicates. But in the case, and also in the case of the junction, below for the 4.8 Kelvin, the junction showed for the zero resistance. So we can succeed in the fabrication of the Josephson junction, niobium copper junction. By using these samples, we measure for the IV characteristic of the junction. This is a very typical, common, the IV characteristic of the Josephson junction. Below the critical current, there's a zero resistance that needs for the superconducting state, and over the critical current, there's a resistive state. But here, this is a very special because for the we measure for this IV characteristic by the spin polarized current by using for this cobalt iron aluminum probe electrodes. So this result indicates for the even that we use for the spin polarized current, the Josephson junction showed for the superconducting state. This result strongly supports for the possibility for the coexisting of the Cooper fields and the spin polarized electrons in this copper layer. And also we have to confirm for the spin transport in this copper layer. As I said, to confirm the spin transport, we measure for the spin signal, no local spin bulk measurement by this probe configuration. By this probe configuration, we can measure for the spin signals. And also, the spin signals have no significant change below and above for the critical current. By this means for the in the below critical charge current, the spin information from the left-hand side can also transfer to the right-hand side, and also the supercurrent can flow from the left-hand side to the right-hand side. These two data, this figure have clear evidence of the coexisting Cooper field and spin polarized electrons in the copper layer. In the final, I'd like to mention whether this is for the spin polarized supercurrent or not. The answer is unfortunately no. We measure for the we also plot for the base resistance of in the non-local resistance. The base resistance is defined by the average of the polarized states and anti-polarized states. The base resistance indicates in this structure, this base resistance showed for the some finite even in the superconducting state, proximity superconducting state. That means for there's some normal current, normal current information also flow from the left-hand side to the right-hand side. So by this result, we can consider in this structure in the copper layer, supercurrent is carried by the coherence electron, while the spin current is carried by the normal electron. But in the case of obviously this spin current is carried by the normal electron, but this is a pure spin current, so the voltage drop induced by this pure spin current is cancelled at this junction. So we cannot measure for any voltage drop in between this normal niobium 2-part, superconducting niobium 2-part. So in this copper layer, we can see for the supercurrent, accompanied with the pure spin current. Then summary and the future prospect. The summary, therefore, as I showed above, the pure spin current was insulated as a normal metal superconductor interface due to superconducting gap. Then also in the same special fabricated structures, we can see that both super and the spin current are found to propagate in the proximity in this superconducting copper layer. In this structure, as I said, in the normal metal layer, pure spin current and the Cooper pair coexist. So this can be the in my opinion, this can be useful for to explore for the spin polarization, the interaction between the spin polarization and the Cooper pairs. Because in this normal metal layer, the normal metal, for example, copper film has not have long spin diffusion length, and also the long coherence length for the Cooper field. So the not necessary to be too thin, the structure. And also the pure speed splitting in this normal metal layer can be easy to tune precisely by the spin injection, by the non-local spin injection. So this normal metal layer can realize for the good platform to explore for the interaction of the spin polarization and the Cooper field. Thank you for your attention.
Yeah, hi, this is Adar Steinberg. I'm wondering regarding the last couple of slides that you showed with the coexistence of normal carriers and proximatized carriers in the copper. And I was wondering whether there's a possibility of looking at the system using something called like a Tinkham-Clark experiment, where you kind of try to see if the superconducting carriers and the normal carriers are in equilibrium. And I have to disclaim that this experiment was done on a superconductor, not on a proximatized region. But is there a possibility that these two populations are out of equilibrium? So you have proximatized carriers which have one potential, whereas you have spin polarized carriers which have just a different potential. And how much can you say about their coupling within your channel?
So you mean for the density of supercurrent and the spin current is very thin, so that this cannot interact. Sorry, what are your points?
But my point is that it's common to look at such systems looking at the chemical potentials of the population. So you can look at the spin-up chemical potential and spin-down chemical potentials, which is like the way you look at spintronic systems. But now you add to this already complicated system a third component, which makes things, of course, much more interesting, are the proximatized carriers. Now, how much can you say about the rate at which these various populations equilibrate? Because it sounds to me that this geometry, I think one has to think very carefully about whether the spin up, spin down, and Cooper pairs are at all at equilibrium with each other. And I'm wondering if you guys have any idea of probing this, maybe using a tunnel contact from the side or something. I don't think it's an easy thing to do.
So you mean how do they consider for the explain for this your question is how to explain for this supercurrent to flow in the equilibrium state, and what the spin current should be flowed in the non-equilibrium state. So the image for the.
I'm saying if you look, for example, at the papers by the Delft group on graphene, Tombros et al. The 2007 papers on graphene spintronics. So the pictures, these papers, the spintronics community uses a certain language, and this language has to do with the spatial dependence of mu up, mu down versus along the channel. That's certain formalism that's used, and generally you can argue that the further away you move from the injection point, the spin, the up potential, the power down potential gradually grow together. Now, here you're doing something very interesting. You add a third population, which is the Cooper population. I wonder if you guys have in any way considered this formalism, consider the fact that your system can simply be out of equilibrium. That's my
I also for the correct. I also don't know for some precise and correct for the theoretical viewing, but the spin current is of course as I said, in the superconducting field, it's described by the chemical potential, the slope of the chemical potential by like this. Then, but also even the superconducting, even the copper layer in this structure. In my opinion, for the pure spin current is flowed in the So, for example, the upspin current for this direction and the downspin current for this direction. By this, for the pure spin current, we can recognize the pure spin current, the flow from the left-hand side to the right-hand side. In the same time that in the supercurrent can be carried by the coherent electron from one naive layer to the one naive part for the another naive part, I think. So this, of course, makes the no drop and not necessary to reach for the slope of the electrochemical potential, because this is for the coherent electron. So in my current viewing, in my current knowledge of this for the pure spin current is flow by the follow the slope of the electrochemical potential, and that is the supercurrent flow the slope of the the difference between the two naive layer. Now we talk.